Welcome, everyone. Today we're going to spend just a little bit more time talking about the chain rule. So we started talking about this in class yesterday, and I want to spend a little bit more time on it just to kind of go over the formula again, just because we're going to see this in a few weeks once we get to exponential and logarithmic functions. So we're going to see this chain rule kind of show up a few more times. And so as we were talking about in class yesterday, this chain rule gives us a way to differentiate the composition of two functions. So that's how we use this. It tells us how to differentiate composite functions. And essentially, a composite function is when we take one function and plug it into another function. And that's what we're seeing right here. This is a composite function because we have one function f, and this is kind of what's happening last. And then we have g of x, which is getting plugged into function f. So as we were investigating, it's helpful to be able to recognize, well, what is the inner function and what is the outer function? So in this case, the inner function is g of x, because it's literally getting plugged into function f. So we want to be able to recognize what the inner function is. And the outer function, well, that's the other one, thing on the kind of the outside. And we also want to be able to identify that. So we have our outer function and our inner function. And what the chain rule does is it tells us how to differentiate their composition. And what we looked at is that this derivative is the derivative of the outer function with the inner function plugged in times the derivative of just the inner function. And so we can almost think of this as like a kind of a process. So the first step is differentiate the outer function. Figure out what that outer derivative is going to be. Then, second step is to plug into that derivative just the original inner function. So we keep the inner function exactly the same. And then the last step is to then multiply the derivative, multiply by the derivative of the inner function. And we've seen this before. We've seen this chain rule before, but we saw a special case of it. And the special case that we saw was our general power rule. And in this case, what we were doing was trying to differentiate a very specific type of composite function where the outer function was a power function. So this general power rule that we've kind of spent some time with is just a special case of the chain rule, because in this case our outer function, why we call it the general power rule, is a power function, x raised to the power r. And so how did we differentiate something like this? Well, we would apply our general power rule. And the first step is to differentiate the power function. And that's kind of what we're seeing right here. We bring down the exponent and we subtract 1 from the exponent, just like we do with regular power rule. So we're just differentiating this power function. Once we have that derivative of our outer function, then we move on to step 2. And we keep the inner function exactly the same. So we keep g of x exactly as is. So that's our plugging in our g of x. And then the last step was to multiply by the derivative of our inner function. Left off the on there. And that's what we're seeing right here at the end. So we have our derivative of g of x getting multiplied at the end. And we're seeing our original function, our original inner function g of x getting plugged in right here at this step. And then we also saw our derivative of our outer function happening, well, kind of two places there because we're doing the power rule. So we differentiated our outer power function, plugged in the original, kept it the same, the original inner function, and then multiplied by the derivative of that inner function. All right, so let's just try an example here. And we'll come back to example 3 for class. But let's look at example 4. And yeah, I think some classes we got to it. We might say a little bit more in class. So let's look at example 4. And here we're going to calculate the derivative of this composite function. And in this case, this composition is composed of the square root of x. And we can tell this is going to be the outer function because it's happening kind of last here. It's happening on the outside. So this is going to be our outer function. And that's because we can see it right here. And then g of x is literally inside the parentheses. It's getting plugged into function f. So that's going to be our inner function. All right, so let's kind of go through the chain rule process. And to help us with this, let's maybe, well, yeah, I guess, our usual trick. When we have a square root function like this, let's just rewrite it as x raised to the 1/2. So, all right, so there's our x raised to the 1/2. The usual thing we do with root functions is rewrite them as power function with a fractional exponent. And all right, what's the first step of the chain rule? Well, the first step is to calculate the derivative of f. So let's do it. We bring the 1/2 down, we keep x the same, and then we subtract 1 from the exponent, so that gives us negative 1/2. And then the second step of our chain rule is to look at this formula, and wherever I see an x, I'm going to plug in the original inner function. So in this case, the 4x squared plus 1, g of x. So I'm going to replace that. And when I do that, the 1/2 is going to stay the same. And then instead of this x right here, I'm going to fill this whole thing in here. I'm going to kind of squeeze it in. And that's going to give me 4x squared plus 1 raised to the negative 1/2 power. So instead of this x right here, what I've done is I've kind of squeezed in the 4x squared plus 1. And then the very last step is to multiply this result by the derivative of our inner function. And so what do we get in this case? Well, we have the 1/2 4x squared plus 1 raised to the negative 1/2, and then we want to multiply by the derivative of this. So let's just kind of calculate that out real quick. Derivative of 4x squared plus 1 is 8x. So derivative of that is 8x, and then the plus 1, constant all by itself, differentiates to 0 there. And so that's what we're going to fill in down here. We're going to multiply this result by 8x. And so what we've done is in this example, and this is our derivative. So what we've done here is we've differentiated this composite function, and the derivative is equal to this 1/2 4x squared plus 1 raised to the negative 1/2 power times 8x. So this last result here, that's essentially our derivative. Now, what we've done is we've kind of used the chain rule to differentiate this composite function where we left these components kind of separated. Now, we could actually just calculate what the composite function actually is first, and then use our general power rule. So let's do this as a check. So we're going to check our answer here by calculating the composite function. We'll calculate the composite function, see what the formula actually is, and then just differentiate with our general power rule. And actually, let's do that. Let's do that up here. All right, so let's check this out. So let's start. Let's take these two components and plug them in, see what we get. So we're going to actually first calculate the composition. Let's get a formula for that. So first thing I'm going to do is replace g of x with what we know g of x actually is. So this g of x here, I'm just going to replace that with 4x squared plus 1. And then essentially what this is saying is take this 4x squared plus 1 and plug it into function f wherever you see a variable. So when we do this, we're going to end up with the square root of 4x squared plus 1. So essentially I'm taking the 4x squared plus 1 and I'm replacing that x right there with it. All right, so this is our composition, and we can use the general power rule to differentiate that. So let's see what we get. We're going to calculate the derivative of the square root of 4x squared plus 1. And what the general power rule says, and probably what we should do just like we did over here, before we start doing any derivatives, let's rewrite that root function. And we'll write it as a power function raised to the 1/2. Then we'll do our derivative. And what does our general power rule say? Well, we bring down the exponent, put it in front, so we're going to put the 1/2 in front. We're going to keep the term that's inside the parentheses exactly the same. And then we're going to subtract 1 in the exponent, so it's going to take us from 1/2 down to negative 1/2. And then finally, we're going to multiply by the derivative of those terms that are inside. So the 4x squared plus 1. We're going to multiply by the derivative of those inner terms. And if we finish that up, we see that we end up with the exact same result. So that checks out. And kind of the reason for why we're going over this chain rule is, and not just leaving it at the general power rule, is the chain rule is kind of the general rule for how to differentiate composite functions. And so we're going to see when we get to exponential and logarithmic functions that there's going to be a similar type process for how to differentiate those types of functions as well. And so kind of having the general framework is going to be helpful, and having that understanding of identifying the inner function and the outer function is going to be helpful. So, you know, generally how we're going to differentiate these things, these types of functions, is probably with these general power rules. But we just want to see that there's kind of this underlying formula that's really telling us how to differentiate these composite functions. And here we actually had the decomposition, what the outer function is and what the inner function is. So we're able to kind of go through this step-by-step approach. All right, so we're going to see a few more examples of the chain rule in class. So we'll see you then. Bye-bye.